Hi, the following is a conversation with Dr. Sabine Ossenfelder. Sabine is an author and theoretical physicist working on the foundations of physics. To be more precise, she describes herself as a phenomenologist rather than a theorist. She's a research fellow at the Frankfurt Institute for Advanced Studies, where she leads the Superfluid Dark Matter group. She is the author of Lost in Math: How Beauty Leads Physics Astray, which explores the concepts of elegance in fundamental physics and cosmology. More importantly, she's an outstanding science communicator who has attracted a huge audience on her YouTube channel, where she publishes explanatory videos on topics related to physics. You can support her work by subscribing to her channel and by visiting her Patreon page, and you can find the links in the description below. This podcast will be also available on Spotify and Apple Podcast, and if you like this, please subscribe, turn on the notification bell, like, and leave a comment. And now, here's my conversation with Sabine. Thank you very much for doing this. Shall we start from your research activities? If you had to choose one of your papers, which one would you select?
I'm a research fellow. I'm a physicist at the Frankfurt Institute for Advanced Studies in Frankfurt, Germany. And I work, broadly speaking, on the foundations of physics. That includes dark matter or modified gravity, this whole discussion, which one is the right explanation, but also the foundations of quantum mechanics. And I have an interest in the philosophy of physics, and I've previously worked on quantum gravity, so it's a fairly mixed bag. Originally, my background is in particle physics, phenomenology beyond the standard model. So I guess if I had to point to one paper, it would be one of my recent papers that I wrote together with my postdoc, Sandro Donadi. And it's about superdeterminism, which I think is one of the paths to make progress in the foundations of quantum mechanics that has been the most neglected. And in this paper, we put forward a concrete model that I hope illustrates how it's supposed to work.
Okay. You run a very popular YouTube channel, and I saw that you started with a mix between explanatory videos and music videos. I was wondering, how would you describe your audience, and what kind of audience are you targeting?
That's right. Originally I did mostly music videos, actually, and then what happened? I was talking about physics every once in a while, and rather unsurprisingly, people were more interested in me talking about physics than in hearing me sing. So I can't blame them for that. Now, the thing is, though, if you mix together two very different things, then the YouTube algorithm just gets terribly confused because it doesn't really know what's the audience to target. So, like in the past half year or something, I've moved the music videos to a separate channel. So what's the channel? So the science channel. What is it targeting now? I think it's broadly speaking targeting people who are interested in science, but not on the rather shallow level that you often find in the popular science press, which I sometimes find really painful. If I read an article about, say, quantum mechanics, just to stick with this example, about some recent experiment that has been done, I'm unable to understand what they're talking about because they have all these, everything's weird, and, there's something with the grin of the cat that separates from the cat, or weird stories like this. And I'm what the heck are they even talking about, And I have a PhD in the topic, right? And so I think the problem is that they're trying to throw out too much of the underlying mathematics. And one doesn't actually have to write down the equations to explain it a little bit with a little bit more substance, let me put it this way. But I'm not only talking about quantum mechanics. I talk about everything that makes headlines, where I feel something has been neglected, something has been overhyped, something didn't really come across the way that it actually says in the paper.
Yeah. And talking about media, I actually read, I don't know if you have the look at this book. It's from Professor Brian J. Ford, and it talks about, it's a satirical book. Basically makes fun of absolutely ridiculous articles on scientific discoveries, published by media outlets. That's why I wanted to ask you, what are some of the most ridiculous and inaccurate articles you've read so far on theoretical physics?
Oh my goodness! Like this story that CERN is making contact to parallel universes. That's like one of the biggest stories. Or what else? Like scientists are creating wormholes in the laboratory. I actually have a video upcoming about this. And I mean, then there are a lot of things that fall more in the conspiracy corner, which is usually not reported by serious outlets, like this whole story that 5G causes COVID, that kind of stuff. These are not really headlines that you find in the normal press, so maybe not exactly what you were asking for.
I remember there was a case of this team of Italian scientists working at CERN that reported that there were neutrinos traveling faster than the speed of light. And that was a mistake.
Exactly.
Yeah. I mean, crazy stories. I mean, because media tends to exaggerate scientific discoveries before they're even published. Sometimes scientists just tell the media, "Oh, we discovered this," but they don't even publish. Maybe they have some submitted paper.
So, I mean, this neutrino story, it was just, I think I would say it was an honest mistake.
Okay.
Like, I mean, they made a measurement and they found that neutrinos travel faster than light. And if I remember this correctly, they very explicitly said, "Look, we think that this is wrong, but we don't know why." And it turned out to be wrong. I have a video upcoming about something else that falls into my territory, which is the idea that the quantum internet would allow us to transmit information faster than light. And this is like a recurring thing. Like this pops up in the headlines every other year or something. And I just think is so terribly embarrassing, because it's like the first thing you learn about quantum mechanics is that it does not allow you to transmit information faster than the speed of light. So I'm like, where do these science writers come from?
Yeah. And that's because this concept of quantum entanglement is always a bit difficult to understand.
Well, it becomes very difficult if you try to understand it without the mathematics, because then you're reduced to using vague analogies that never really actually work.
So you wrote this great book. I really like this book, Lost in Math. And I wanted to ask you, what's the motivation behind this book?
Well, I explained this to some detail in the book, right? That I became very worried about what's going on in this research area, which is mostly the book is about physics beyond the standard model, high energy particle physics, but also quantum gravity, and a little bit about quantum foundations. And maybe astrophysics, some parts of astrophysics where we're dealing with this dark matter, modified gravity dichotomy. So all these areas have problems that have been around since the 1930s or something. We have known of dark matter since the 1930s, and quantum mechanics has irked people ever since someone came up with it. We've known about the missing theory of quantum gravity also since the 1930s. So these are all not new problems, but we've made basically no progress on it. And yes, you could say that until the 1970s, where the standard model was completed, things seemed to move forward, right? So we moved on from quantum mechanics to quantum field theory and to Young-Mills theory and to the standard model, with finally the last outstanding particle, the Higgs boson, being discovered in 2012. But these big problems like the measurement problem, the missing quantization of gravity, dark matter, and so on have remained unsolved. And it's not for want of trying. There are lots of theories that people have put forward, but they've, to the extent that they made any predictions at all, these predictions have all been falsified. And what I've seen is that even though these predictions were falsified, people in these fields did not revise their methods. They're still working by the same methodology that has not worked for 40 years. And so basically, what my book is about. It's asking people like, why do you do that? If we see so obviously it's not working, why do you continue to do that? So when I set out writing this book, I wasn't really sure what I would find. I just I wrote to people and asked them like, can we make an interview? Why do you think this would work? And people gave a variety of answers. Mm-hmm. And in the end, my conclusion was that the major reason they continue doing this is because that's what they have learned. Okay. And there's very little self-reflection in the field. People are not actually looking at the history. They're not asking, is this even a good methodology? They just continue doing what they've been told by their advisors, who took it from their advisors, and so on. So basically, I think it's a community problem. And with this book, I was trying to draw attention to this.
Yeah. And at page 197, you wrote that several well-meaning friends have tried to dissuade me from writing this book. Why is it controversial?
Well, it was not so much about this particular topic, though there was certainly part of it. It was more that they tried to dissuade me from writing a book in the first place, because I'm not tenured. I'm still not tenured. And the general rule of thumb is do not write a popular science book before you have tenure. Because, and that's certainly to some extent true in Germany, people will not take you seriously as a researcher anymore. They'll think you're now doing science communication. And, I guess I'm just not very good with taking advice.
You've done a great job with both.
Well, as I just said, I'm still not tenured, right? So I sit on a temporary contract that will run out next year. So, there are two sides to every story. Looks good from the outside. From the inside, it was, for what my position is concerned, it was not a great success. But it was really important to me because I think that this progress in the foundations of physics is like super important for progress in science overall. So I guess you could say it was more important for me to try to do something about it than to secure a cozy position.
Which always involve lots of politics, by the way. It's exactly. Not only the science, there is lots of politics behind these appointments and all these things, as far as I'm aware.
And honestly, I think it kind of corrupts you, right? Yeah. Because once you start playing the game, you're kind of bound to it.
Yeah. And so you went around the world and you interviewed so many people. I wanted to ask you, how was the experience? You went to so many places, and did you have a crew with you? Did you film the things, or you just carried the audio recorder? How was it?
Yeah, it was just me, and I never interviewed someone before. It was somewhat of an experience. I bought a recording device, and I had to figure out how to use it, and then. Of course, it broke down at some point because I forgot to charge it. And I think it was in the interview with Frank Wilczek. So we actually had to record the thing on his phone, and then he had to send me the recording. And I felt terribly incompetent, let me put it this way. But it was interesting, I think I've meanwhile learned how to interview people. I think I've made some progress on that. But really, you notice this in the interviews if you read the book. It's like all of them, with the exception, I think, of Weinberg, knew that I'm a physicist myself and I do have a PhD and I've worked on the foundations of physics. And you notice this in the interviews, the way that they explain things. It's not as fluffy and vague as you would explain it to someone who doesn't have any idea what's going on. So I think this adds somewhat to the character of the book. It's not so much a journalist going around asking the always same questions. It's more like me trying to understand what other people are doing. And to some extent, the reason I chose this format was that I wanted to have other opinions in the book without, trying to summarize them myself. So I thought the easiest way to do that would just be to actually let people speak for themselves.
My feeling from reading this book is that it provides a great overview for theoretical physicists on some of the main issues in theoretical physics, but it also provides an entertaining reading for the general public. However, from the perspective of a physicist and an engineer that knows almost nothing about these topics, I said I wish I could have actually read the actual theories she's talking about. So if you had included the actual math and physics, I would say for dummies in the book, what would have been the size of it?
Yeah, I mean, it depends on where you start. Like, if you actually want to explain it all, you have to start with underground physics, right? And then it becomes very bulky. But maybe I should add that I actually do have a somewhat more technical paper to go with it. It does not have a huge amount of equations, but it explains this whole issue of naturalness in a little bit more detail. Yeah, it's mentioned in the appendix. It has a reference to the paper. It would have been a much longer book, and it would have been rather indigestible. I think that it's a tough enough sell. Theoretical high energy particle physics is not for everybody, even without the equations. And of course, I've tried to make it as engaging as possible, but at some level, they're just some things are just not easy.
Yeah. Have you thought about doing a documentary from your book?
Well, I'm not really sure what you have in mind.
Like, you go around, you interview the guys, and then you film the journey and everything.
Well, I didn't film it, right?
Yeah.
And at least one person has meanwhile died, so it would be pretty hard to. Polchinski died.
Yeah, I mean, there are similar works. They do documentaries on these topics, and I think it would do it's a great starting point, I think.
Well, I'm a terrible actor, so I guess they should find someone else to do it.
Well, you don't need to act. People would want to see yourself doing this, like going around and doing these interviews and so on.
Yeah, you know what? It's actually really hard to be yourself in front of a camera.
So now, one thing I find hard to understand are these concepts of simplicity, beauty, and naturalness that you mention in the book. I mean, I never heard of these terms in applied physics, material science, and engineering. So what does it mean that physicists rely on beauty, at least the physicists that work on particle physics and theoretical physics?
What I'm explaining in the book is that in the foundations of physics, people have come to use very specific notions of beauty. And those are not exactly your everyday ideas of beauty, where you would say, well, a sunset is beautiful, or those flowers are beautiful, or that kind of thing. It's a very rigorous type of mathematical beauty. And they're just applying this to the new theories that they develop. So the new theories have to be beautiful in a very specific kind of way. The brief summary of the book is that I'm saying where you're putting the carriage before the horse, right? Yeah. You should not start with assuming a specific notion of beauty. You should try to find out what nature is telling you, and then you will find beauty. And it may not be the beauty that you expected, but we will come to find it beautiful just because that is what has happened historically. So these ideas of beauty that physicists are using in the foundations of physics now, one is simplicity in an absolute sense. So I don't mean Occam's razor, which is really a comparative judgment, when you say, okay, so I have two theories and they both describe the same data to the same accuracy. I take the simpler one. So that's a good scientific criterion. I mean that in the foundations of physics, scientists are urgently trying to find theories that are simple in an absolute way. And one area where this is particularly obvious is this quest for a unification of the forces, or even a theory of everything. So that they just have this assumption that as we look deeper into the structure of matter, it has to become simpler. And I'm like, well, why? Why does it have to be the case? Why can't it be that maybe it gets more complicated again? We actually don't know why you're making this assumption. It's not justified. And so philosophers would call it a metaphysical commitment. You should just make this assumption, but it's not based on evidence.
Is it inductive reasoning?
Well, no, it isn't. That's exactly the case. I mean, it has not. That's exactly the point. It's like historically, it's not been the case. You could have said, well, take who was it? Aristotle. I keep mixing up the Greeks with this theory of the four elements.
You have it in your book, right?
Yes, in the book, right. I've drawn this great diagram myself with the four corners, and so that was a simple theory. And you could say, well, this whole story with the, 109 elements in the periodic table, that's much more complicated, right? And then you get to quantum mechanics, and you may think, well, now things get simpler again. And that's right, up to the point where you notice, well, there's this thing that's called the weak interaction. And then there's quantum chromodynamics. And quantum chromodynamics spits out all of these mesons and bosons and so on and so forth. And it makes things more complicated again. It's never been just a path to simplification. It's always been ups and downs.
Yeah.
And so I'm like, well, maybe the next step is an up and not a down. Okay, so that's the simplification, and then there is this naturalness criterion. So naturalness is basically the opposite of fine-tuning. So these two words they belong together. A theory is natural if it is not fine-tuned. So people use this basically as synonyms. But in particle physics in particular, they're using a very specific notion of naturalness that's called technical naturalness, which is a little bit different. But the idea is basically that a theory should not have improbable coincidences. In principle, that's a good idea, and there are certainly examples where this is a good criterion. But the problem is that in the situations where physicists apply this criterion in the foundations of physics, there is no way to ever arrive at a proper probability distribution. They just assume it. So they're creating the problem by assumption. And I'm saying, well, that's not, you can't conclude anything from that. You've created the problem by putting it in. And indeed, it's easy to remove these problems just by putting in a different probability distribution. So the point that I'm trying to drive home there is that these are not actually problems with the theory. It's just that you don't like the theory for one reason or the other. And again, philosophers would say, well, that's a metaphysical criterion. Okay, so you can say, well, for some reason, I don't like theories which have this property. Therefore, I don't want to work with them. And yeah, you can do that. But the problem is that physicists in these areas, that they don't really realize that this is what they're doing. So this is why the book's called Lost in Math, because they put these requirements into the mathematics, and then they forget that they were just metaphysical assumptions.
Yeah, so they like something and they decide to go along with that thing they like, which is all these concepts that are not found anywhere in science. They're just coming from experience because maybe it worked sometimes, and they decide, okay, we want to go along with these concepts of beauty, simplicity, and naturalness because it worked maybe for Einstein and other similar scientists. So they think it will work in the future as well. Is that correct?
No, it's not. That's the irony about it. If you look at the history, you will find that actually arguments from beauty didn't work. It's just that the only cases that physicists seem to remember are the cases where it just, I would say, coincidentally did work.
Okay.
Like, for example, and then you can ask how relevant was it actually practically in the development of the theory. But it's certainly the case that Einstein and Dirac and Weil and some others went on and on about how important it is to pay attention to beauty and so on. But there were also a lot of physicists who went on about the beauty of the theories, and those theories turned out to be wrong. So it's like you're not looking at the control group if you're trying to make that kind of argument.
It's cherry picking.
Yeah, it's cherry picking, exactly.
Yeah.
And it's the same with these arguments from naturalness. Arguments from naturalness have failed over and over again. Like they used naturalness to predict this particle called the axion, and that was falsified in the 1970s. Now, I should add here that they are still talking about a particle called the axion now. This is not the same axion. This is what was originally called the invisible axion. Okay, so it's a variation of the original axion that was invented to avoid the constraints from the experiments at the time. And, you know, the cosmological constant is not natural. It just isn't. And the Higgs mass, for all we know, is also not natural. So you have this series of failures, really, but still they cling on to this criterion, which is, I think it's just bad science. You know, if you notice that your methods aren't working, you're supposed to revise them, and it's not happening.
Yeah. And what would be an example of a beautiful and an ugly theory?
Of course, I have to emphasize this again. This is only according to these criteria that physicists are using right now. So I would say, well, you have to make your personal judgment. But if you use these criteria, then this theory is beautiful and this is ugly. And an example would be supersymmetry. Supersymmetry is widely believed to be a beautiful theory. It goes very nicely together with unification. It has this additional symmetry. It's natural, technically natural. Okay, so people like it. It also has this element of surprise. I go on about this for a little bit in the book because it was, there was this theorem that said a theory like supersymmetry should be impossible. But then people found a loophole in this theorem, and so everyone was like really excited about it. Oh, sorry about this. Okay. So supersymmetry scores very highly on all these criteria, which is exactly why physicists think it's such a good candidate theory. They still believe it, even though it's run into conflict with experiment over and over again. A theory that a lot of people consider to be ugly is modified gravity. There are various theories of modified gravity, and I guess they consider all of them ugly. Now, why are they ugly? Well, if you look at the mathematics, it just doesn't have the form of the theories that they are used to. This is something that I actually work on myself for a little bit. These theories for modified gravity, they are more similar to certain condensed matter theories than they are to high-energy particle physics. And the people who work on high-energy particle physics, astroparticle physics, and so on and so forth, they're not very familiar with this condensed matter physics type of thinking. So to them, it's ugly. I think it really has much more to do with familiarity than it has with aesthetics.
I don't know. Who cares? I mean, as long as it works. Who cares about beauty? I don't understand this thing. So now the other thing I wanted to ask is that from the perspective of an experimental physicist or a material scientist that is used to work with experiments that can be easily set up, theoretical physics seems a rather depressing field in the sense that it must be difficult to find motivation when working on something that can't be tested. So how do you know if it's ever possible to test your theories? How can you know that?
Yes, before I answer this question, I have to address one point. You just said theoretical physics must be a rather depressing field or something like this. But theoretical physics is not specifically only something in the foundations of physics, but actually most areas, research areas in physics do have a theory part.
Oh, yeah.
And in most of these areas, like for example, condensed matter physics, certainly there's theoretical condensed matter physics. But people confuse this all the time.
That's right.
I noticed this, and you know probably it was a slip, but it's a good occasion for me to go on about this.
You're right. Yeah.
I actually made a video about this, like what is theoretical physics, but people didn't watch it. So, but now I have had opportunity to explain this. So in the foundations of physics, in particular, maybe I should add that actually I would describe myself as a phenomenologist, not as a theorist. What does a phenomenologist do? The obvious next question is, phenomenology sits somewhere between theory and experiment. So people who work on phenomenological models try to make contact between the fairly math-heavy theory development and what's actually possible to experimentally test. It's kind of a lot of people who work on the theory side don't really appreciate it, how important it is to actually pay attention to what is experimentally possible. So, for example, for some time, as I mentioned, I worked on quantum gravity, and a lot of people, especially the theoreticians, tend to think that that's just something that can never be tested anyway. To which my response would be, well, then why are you working on it? Aren't you supposed to do science? If you don't think it's actually testable, why is it interesting? So I've actually asked a lot of people this, but a lot of them come from this very math heavy philosophy where they actually believe that if you get the math sorted out, then the theory has to be correct. And I'm like, no, that's just never been the case. There might be many ways to solve this, to resolve this inconsistency between quantum field theory and general relativity. And in the end, we'll still need experiment to figure out which one's the right one. And So I have tried to find ways to probe consequences of these approaches to quantum gravity that seem to appear in most of these theoretical approaches, like, for example, the existence of a fundamentally minimal length scale. This is something that comes up in pretty much all approaches. It's kind of a regulator, basically, for the infinities. And then you can ask, well, what would a phenomenological model look like that has this property? So I'm not taking the whole complicated thing, string theory or loop quantum gravity or causal dynamical triangulation or what have you. I'm only taking this one assumption. There's a fundamentally minimal length scale, and I built a model with that. And then you can look for consequences of that. So maybe that's a bad example because in that case I came to the conclusion you can't measure it. But I looked at a few other things, like, for example, if you believe that space-time is fundamentally discrete, so there's something that people like to call space-time atoms, though I find this somewhat misleading. It's really you have a certain finite scale and kind of a coarse-grained description of space-time. Then on this fundamental level, you would have violations of certain symmetries that can have experimental consequences. They would affect, for example, how particles propagate through space-time. And then, roughly speaking, they would scatter at the impurities in this discretized space-time. Yeah, I wrote a paper about how you could test this, but I don't think anyone has actually done that. There's some other things that people have thought about how you could test quantum gravity that I myself don't work on. I have not worked on, for example, with the cosmic microwave background with heavy quantum oscillators. So I'm particularly excited about the last one. So personally, I think like that this is a path to a Nobel Prize, and I don't understand why people are not more interested in it. There are basically no predictions for that kind of experiment from the theory side. So I find this a somewhat perplexing situation. So yeah, but maybe to come back to your question, how do you not get depressed?
Yeah.
Well, I guess I get not depressed because I'm trying to find ways to actually test the theories.
That's right, yeah. And in your book, you also mentioned crazy setups, like I think you mentioned a detector of the size of Jupiter orbiting a neutron star or something like that, and a particle accelerator of the size of the Milky Way. What are those things for?
So, if you naively try to estimate at which energy scale in a particle collision the effects of quantum gravity would become as strong as the effects of the other interactions, then you get something that's called the Planck energy. Which is like 10 to the 15 tera electron volt or something. And so the Large Hadron Collider, was it 10 to the 16? Well, something like this. And the Large Hadron Collider reaches around 14 or something tera electron volt. So there's like this 14 orders of magnitude gap between what we can presently do in an experiment and the energy scale that you would need to reach to produce an appreciable number of gravitons, say, so that you could actually measure them. And then there's the question like, what would it take to actually build a particle collider that could reach this energy? And this is when you get this estimate with the size of the Milky Way. This is assuming you use the technology that we currently use for the Large Hadron Collider. So you just scale this up. And the story with the detector the size of Jupiter is what size would a detector need to have to detect individual gravitons? And you can do that if you have a detector the size of planet Jupiter. If you put it in orbit around a neutron star and then you wait for 10 years, something like this, so you get all these completely ridiculous numbers. But as I was just trying to say, I think that these estimates are very misleading because there are entirely different effects of quantum gravity that are much easier to observe. So you don't necessarily need to actually produce or measure gravitons to find evidence for the quantization of gravity. It's like you don't actually need to detect single photons to find evidence for the quantization of the electromagnetic interaction. You can see this, for example, in the spectral lines in atoms, or just by the existence of atoms, basically. You need electromagnetism to be quantized. Otherwise, it just doesn't work.
So you would need to observe gravitons, you would need to observe quantization of gravity.
No, what I'm trying to say is that if you could detect individual gravitons, that would be evidence for the quantization of gravity, without doubt. But there are easier experiments that you can do that would be indirect evidence for the quantization of gravity. And those experiments do not require that you actually reach these high energies. For example, as I like to point out, one of the most obvious facts about gravity that we all know of is that it becomes stronger if you have larger masses. That's why gravity, even though it's fundamentally the weakest of the forces, it's the one that survives in everyday life. Like the reason I don't float off is gravity. Right? And why is that? Well, it's because it in contrast to all the other interactions which neutralize, gravity just adds up. So this idea that gravity is just too weak to measure the quantum effects doesn't work. The actual problem is that if you add up the masses, you get larger objects, and it's hard to maintain the quantum effects for the larger objects. But that's a research area where there's a lot of progress being made, where people are putting larger and larger and heavier objects in quantum superpositions. And at some point, you just reach a regime where you might be able to indeed measure the gravitational field of these things in quantum states, at which point you can just measure what happens with gravity in that case. And we're not quite there yet. Like there's still, last time I looked, it was like 4 or 5 orders of magnitude. But we're not talking about 14 orders of magnitude, and that's an area where there is a lot of progress in the technology development right now. So I'm carefully hopeful that in my lifetime we might actually be able to measure the quantum effects of gravity.
Okay, yeah. So and so this is about looking at gravitational effects in macro-scale quantum systems, like maybe Bose-Einstein condensates or things like that.
Well, Bose-Einstein condensates are not heavy enough. Usually these condensates, they may contain like, in the biggest condensates, you have something like 10 million or so atoms. And if you add up the masses of this, it's not a terrible lot. Atoms don't put a lot of weight on the scale. I'm more talking about actually tiny discs. Usually they use discs, silicon discs, that you put in some kind of cavity and bombard it with a laser. So the discs takes on these quantum properties that from the momentum transfer from the laser. And the idea is that you can but as I say, that's only like roughly the idea, maybe. So they're not quite there yet. It's not working as I hope it will at some point. You might be able to actually bring these tiny things. So right now they are reaching masses like something like a nanogram or something, but you need to get to something like more like a milligram into superposition of different locations, or maybe it might actually work with superpositions of energy levels or something like this. And then you can try to actually measure the gravitational field of that quantum state. And there are some other experiments that people have thought about. For example, one that's called an entanglement witness. So the idea is that if you can show that the gravitational interaction is able to entangle different objects, then that would prove that gravity itself also has to be a quantum force.
Right.
So this is also an avenue that people are pursuing.
It's a cool subject. So I'm going to ask you a question about synchrotrons, because I've done lots of work on synchrotrons. There are tens of synchrotrons worldwide which are used every day in a variety of fields, including applied physics, chemistry, material science, medicine, biology, and even archaeology. And the circumference of the European Synchrotron Radiation Facility, the ESRF in Grenoble, is about 800 meters. However, there are larger synchrotrons that exploit similar functioning mechanisms, but where instead particles are collided. So CERN's Large Hadron Collider is the world's largest and highest energy particle collider. It's 33 times larger than the ESRF. And my understanding is that with the LHC, we've only managed to confirm the existence of the Higgs boson. Is that correct?
Well, it depends on what you mean by discovery. I mean, the Higgs boson was certainly the biggest discovery that made the biggest headlines.
Right.
But I mean, they've learned a lot of other things. For example, about the structure of the proton. Like, it's kind of, if you bang protons into each other, it's kind of impossible to not learn something about the structure of the protons. And they also have a heavy ion program, right? So they learned something about heavy ions. I'm sure about this. I've heard some talks about it. Please don't ask me about the details. And they've certainly, and they've seen a few new composite particles. I mean, not fundamentally new ones like the Higgs, but some new mesons, that kind of stuff. So yeah, I mean, as I say, there's a lot of physics that's coming out of it. But for what progress and the foundations of physics is concerned, I would say that, yes, the Higgs has been the only discovery.
Has the LHC been able to deliver what physicists had promised in their proposals?
I don't think they promised anything. Like, I can't believe that they would do that. Certainly, I mean, this is an exploratory experiment. You can't promise that you will find something. But I can tell you that from the theoretical side, the discovery of the Higgs was kind of, and I will qualify this in a moment, a sure thing, in the sense that we knew the standard model would just stop working at the energies that the LHC can test. So it's this whole story with the unitarity bound from the W scattering. So we knew something had to happen at these energy scales, and the Higgs was the simplest explanation. There were different explanations before the LHC, but the Higgs turned out to be the right one. So in that sense, the LHC was a safe bet. But they certainly also thought, and you find this documented all over the place, and I've actually collected references because now no one wants to have said it. But before the LHC turned on, people said over and over again it would find supersymmetry, it would find dark matter candidates. Those were like the biggest things that a lot of theorists were pretty sure about. And the reason were these arguments from naturalists that I just explained are unscientific.
And so were these kind of, how to say, predictions put in the proposals for the construction of the LHC? Because, I mean, before you can build such a facility, that facility costs like $10 billion or something. You need to put a big proposal in front of the policymakers and all these guys to get the funding.
Yeah, I guess. I mean, it shouldn't be hard to find this in the CERN archives. In all honesty, this was all before my time, basically, because I remember when I was a student, so that was in the mid-1990s, they were already talking about the LHC. The LHC was about to come, and then it was postponed, and eventually it did come. So exactly how they sold it, I've no idea, but I'm pretty sure that the failure, like the theoretical failure of the CERN model, must have been like the most important point. But as I said, there was also this naturalness story about new particles, like for example supersymmetry, and then for some time there was this whole story with the extra dimensions, and which led to this micro black hole thing. I don't know if you remember this.
Yes,
this
yes.
all makes me feel like really old. Yeah.
Where is it? Martin Rees talks about that. I think it was.
Yes, in this. I read this book.
Or
yes,
in the other one, where it talks about potential risks from the creation of a black hole in the collider.
Yeah, exactly. I mean, as I literally wrote my PhD about this.
Yeah. Okay.
Yes. I mean, not about the risk assessment, but about the production of microscopic black holes at the Large Hadron Collider. So I could tell you exactly why it was extremely implausible. But I mean, these are not obvious reasons. Actually, the whole reason for me writing this book ultimately goes back to me thinking this is extremely implausible. Why is it implausible? It's because it was based on this argument from naturalness, which is not a scientific argument. But at the time when I wrote my PhD, that wasn't clear to me. I actually think that one should take these things seriously. And I think CERN did very well with this, with doing their risk estimate and looked at other evidence, from similar energy scales, like from the cosmic rays and all this stuff with the cross-section and the rapidity distribution, and so on and so forth. So I actually think they handled it well. Who did not handle it well was the press. Because they kind of rather carelessly, I would say, tried to make it sound more dangerous than any scientist thought it was. And a lot of people got really, really worried about it. Like they were really afraid. And for a long time, I saw this when I gave lectures. Like people would come to me and say that they're scared that the world will end when they turn on this thing. Yeah. And at some point, I think the media kind of got it that it was really irresponsible what they were doing, and it kind of ceased. But for a couple of years, that was really a running theme.
And would you support the construction of a larger collider? Because there are plans to build larger colliders in Europe and in China as well. What's your view on that?
Well, I'm not in favor of it. I guess I'm like, I find it funny you'd ask, because I guess if I'm known for one thing, it's because I'm critical of the idea of building a next larger collider. Yeah. It's somewhat of a shame. There are very few physicists who want to speak out about it. I've talked with a lot of physicists, not particle physicists, but physicists of other areas who are like, I'm totally with you. You know, this is just, it would be a waste of money. While we're doing this, we can put the money into better things. But no one wants to be quoted on it. So I've kind of become the face that people attach to it. And I think it's not good. We should just have a broader discussion about it. And, I've explained this over and over again why I think it's not a good investment. But basically, you've already touched on the main point. Like there's this big gap in the energy scales. If you try to actually get there by pumping large amounts of energy into a collision, you need to bridge a gap of at least 10 orders of magnitude, optimistically. And building the next larger collider is, it may get you, it doesn't even get you a factor 10. It's kind of something like a factor 6. And it would cost like 20-40 billions of dollars, depending on whether or not you actually count the operation costs. And for what? Right? They're just better things that we can do with this money. Certainly seeing the situation that the world is in right now with this ongoing pandemic and climate change and all that kind of thing. I actually think it's irresponsible to put that amount of money into a machine like this, which would have no tangible benefit, not even for the foundations of physics.
So where would you put the money if you had to choose? If you could choose, if you were a policymaker, where would you invest?
People ask me this all the time,
right,
and I always give the same answer. It's like, no, it's fine. It's just that, the thing is that I wouldn't make such a decision myself, right? Because there are lots of things that I don't know. Of course, I do have opinions myself. But I would make sure to collect information from as many people as possible. Unsurprisingly, personally, I'm most interested in the research areas that I work on myself, which would be experiments that would allow us to more clearly distinguish between particle dark matter and modified gravity. And I wrote some papers about that. Certain avenues in the foundations of quantum mechanics where you could actually test superdeterminism, which is what I briefly mentioned at the very beginning.
Okay, now you spoke about quantum gravity. When I think about quantum mechanics, I think about the possibility to control electrons and photons. Is it the domain of science fiction, the possibility to control gravity the same way we control electromagnetism?
Well, it certainly is right now.
Okay.
We would have a long way to go to change something about this because of this big gap in the energy scales. So we would have to develop a lot of technology in between. I don't think it's entirely impossible, but it's a long way to go.
Now, one thing I want to ask you, because you mentioned artificial intelligence, and you said at page 133 you wrote, I try to imagine the day when we'll just feed all cosmological data to an artificial intelligence. Is there any work done in terms of development of new theories using artificial intelligence?
Not as much as I would hope. You may have seen that Max Tegmark published a paper like a year ago or something, or maybe it just recently got published and was on the archive a year ago or something like this, where they are using artificial intelligence to discover equations of motions for certain systems, like the chaotic double pendulum, or I can't remember exactly what examples they had. And I think that's a very interesting area of research because it opens the possibility that at some point we may just, as I wrote in the book, we just take all the data, all the cosmological, astrophysical data that we have, and we stuff it into an intelligent machine, and it will spit out, the best equation of motion that it can come up with. And I actually think that we should be able to do something like this when it comes to the question of dark matter versus modified gravity. I basically think that the data have been telling us for a long time, like at least 20, if not 30 years, that the best explanation for all the data together is a hybrid theory that sometimes looks like cold dark matter and sometimes looks like modified gravity. And that in and by itself doesn't really tell you what it is. But I would say that's kind of a phenomenological model. And that's a better model than just modified Newtonian dynamics, which we know doesn't really properly on its own, doesn't really do the job. But we also know that cold dark matter has its shortcomings, especially when it comes to galactic scales, like it has a variety of problems there. And where we don't really know what to do is to figure out where to draw the boundary. Like, where do we use the one theory? Where do we use the other theory? And I think that a suitably programmed artificial intelligence should be able to do that. It's just something that no one's doing. So I'm not really much of an artificial intelligence person. Artificial intelligence needs a lot of data to train on. And there isn't actually all that much data in astrophysics. It's like you think there is, but if you actually look at what it is, it's compared to particle physics, it's nothing, like nothing really. So I'm not sure if we're quite there yet, but in principle, I think it can be done.
Mm-hmm. Yeah, so I'll change a bit the topic and discuss briefly about the publishing business. There is a huge pressure from universities to publish. Like sometimes they have these rules that you, in some places, that you need to publish a certain amount of papers and so on every year, and so it's becoming like a sort of popularity contest. Do you think this is distracting? Do you think there should be a different model? I mean, in the past it used to be different, but I think this kind of policies where you need to publish and publish and publish came out after 2000 or something like that. Before it was different. Before people used to publish only when they had great results.
Yeah, so it's certainly a bad development. I'm not entirely sure which universities you're referring to. I am aware that especially the United Kingdom does these research evaluation exercises like in regular intervals. And I know that researchers in, I think, China and some other countries, they're actually paid a bonus if they publish a paper in a big journal, that kind of thing. So those are really, really bad ideas. What is this?
I got that, what you're talking about. I had it open. So if you publish in Nature, in 2016, they would pay you $43,000 for a paper in Nature.
Oh, yeah, well, that's interesting, yeah. Though I read recently, I think it was in Nature News or something, they're thinking about doing something about it. It's clearly a bad idea. I mean, look, we all know what the result is. Like, people will try to publish something that's catchy. It doesn't really matter if it's wrong or right, right? That try to get it into a big journal and hope that no one notices if it's not the best research. And this is happening all the time. And so it just sets entirely the wrong incentives. To some extent, I have to say that in the Foundation of Physics, we're kind of lucky that journals like Nature and Science tend to not publish papers about the foundations of physics, because at least that's a problem which we don't have. Generally, the idea that you can evaluate research by very simple numbers, like counting the numbers of papers or the number of papers that have been published in this or that journal, or the number of citations and so on, is like complete nonsense. And I'm not only just saying this. There are lots of papers that have been written about it in fields like sociology of science, scientometrics, and so on. People are discussing better measures for scientific impact. And actually this research evaluation exercise, or whatever it's called, I think they don't use quite as dumb measures as that. There's a little more diversity in that, which I think is a good thing. But it's still a problem. Like, people pay a lot of attention to how many citations they get, where they can publish their papers. And the result is that they tend to focus on certain research questions that will allow you to do that. And that's typically stuff that a lot of other people also work on. And that just contributes to this streamlining effect, where people continue to do the same thing over and over again.
So this would be inflated fields.
Yeah, basically, yeah.
Like a
Like
graphene
kind of like
or
research bubbles.
graphene used to be one of them. What else? Well, I used to work in perovskites.
Well,
That's
yeah,
another
I
one.
mean, in some areas, like when it comes to some things that have a lot of societal relevance or a lot of technological potential, the problem is partly caused by governments or research agencies pouring money into certain research directions, and that's just a political thing. So I would say that I think that they don't really take into account very well that this will give them diminishing return on investment. You're just forcing more and more people into an already overcrowded area.
Exactly,
And
yeah.
this is not a good idea. On the other hand, I'm like, well, if they know what they're doing, then that's what they're doing. Right? I mean, like if there is a lot of public pressure to do more cancer research, then that's how it is, you know. Then you can complain, okay, maybe that's not the most efficient thing we could be doing with the money, but if people think that that's what we should be doing nevertheless, then that's how it is. So this is not exactly the problem that I was talking about earlier, which is really a self-generated problem in these research areas where people pay a lot of attention to what other people are saying.
Yeah. Now, coming to the research grants, at page 155, you mentioned that there was a study where some participants in the study referred to the impact statements in the research proposals as made-up stories. Can you give us an example of a typical research proposal and how are these goals defined and what are the sort of deliverables and how are these assessed by the committees before they award a grant?
Well, so I remember this study, which I mentioned in the book, but I can't remember exactly what these people were referring to there. Like what the research areas were that they worked on. I mean, what I can tell you is that in my research area, a lot of this talk about the supposed impact is just empty blah blah, because you know we're doing the kind of research that, if we're lucky, will have societal impact in 1,000 or maybe 2,000 years. It's like it's more difficult to predict the relevance of this research than it is to do the research itself. So what a lot of people do is that they repeat the always same motivational stuff. For example, something that I've worked on for a bit is this gauge gravity duality that now a lot of string theorists also work on. And one of the stories that everybody likes to point towards is that you could use it to understand high-temperature superconductors, which would have some applications. And that's not, strictly speaking, wrong, okay? But there's also no good reason to think that it will actually work out. And I think everybody who writes that kind of thing knows that this is like really, really far-fetched, but you have to put something into this section of your grant proposal. And I think it's pretty much the same in all other areas. Like, you have to put something in there, and it has to look good, and it has to sound really, really important. And then, you know, everybody else is doing the same thing, right? Yeah. So it's like you're shouting on the fish market, my fish are the best fish, buy my great fish. And so it's just, yeah, I don't know why they expect people to do that. It's like, I kind of feel that this part of the proposal is something that should be written by someone else. Like you write your stuff about your research area, and then someone else is supposed to evaluate how important this really is.
Yeah, so you're basically saying being honest doesn't really pay back. You need to be able to sell this. You need to make people
that's
dream.
Exactly the problem.
That's the thing I wanted to ask you is about page 156. You say that in summary we have more people better connected than ever. who face increasing pressure to produce in specialized subfields with less financial security over shorter periods, which is kind of depressing. Why do you think researchers' positions aren't paid enough in academia compared to other jobs that require similar skills? And is there anything that can be done to change the current situation?
More money, but where's the money supposed to come from? So maybe I should say that this sentence which you just quoted, that's a summary of me going through various statistics and data and so on and so forth. So and all the references are in the book. A lot of academia thrives on cheap and easily replaceable postdoc positions, and those people are basically burnt through. I think I'm allowed to say this because technically I'm still a postdoc, and so they're just. I guess it's all supply and demand. There are just so many people queuing up for these postdoc positions that you can keep the salary really low. And even if the salary is okay, then fairly often these may be positions without benefits. So there'll be scholarships, usually they're tax-free, which makes them super cheap for the institutions. But then the people will not have health insurance, they will not have life insurance. If someone happens to get pregnant, that's a problem. And so they're not good jobs to have. And for example, I mean, I've had like a whole series of these positions. And one of the problems which you only notice as you get older is that they don't have any pension plans. Yeah. Right. So it's one of the problems that you pile up. Other people my age do have some kind of pension plan. I've pretty much lost like 15 years of my life. And, maybe that's a very German thing to worry about. But I mean, it matters to me. And yeah, I mean, what can be done about it? There are lots of proposals that people have made. For example, one thing that comes back over and over again is that we should be stricter in deciding early on how many people we should allow to even continue into postdoc positions so that pretty much all of them could land on a tenure place. It's just not workable because the people who are now on these tenured positions, they live from these cheap postdocs. So they're never going to approve it. There are certainly things that you can do about the benefits, and especially in Germany, as I keep saying, maybe that's a very German thing. So for the Germans, this is like really important. And I also know that this is a thing in Sweden, so I've been in Sweden for like 6 years. The national funding agencies have a policy that they will only fund postdocs if they have decent employment contracts. So if you get money from them, you're not allowed to put the postdocs on a scholarship, even though in that case you might be able to hire twice as many people. That's roughly as a rule of thumb. That's the difference that we're talking about. So there there are little improvements here and there, but I guess the big change isn't happening.
Yeah. Okay, so I think we can close it here. And I would like to thank you for your time. And please, guys, have a look at this book. It's a great book. And Sabine.
And it's now it also has a paperback version now.
Yeah. Okay. So thank you very much for your time, and have a great day. Thank you.
Thank you.
Thank you for listening to this conversation with Dr. Sabine Hossenfelder. If you enjoyed it, please leave a comment below, like, subscribe, and turn on the notification bell. And please support this channel on Patreon. And thanks for watching.